So last time I described the Newton method. For fixed points. And a point is fixed if there is a map that takes it and maps it into itself. Totally simple. So that you can write as 0 of a function of x equals x minus f of x. And we can expand this function we can assume that we know where the 0 is, so we can expand it around the 0. And I'm using this label to denote the fixed point, just because we use P to denote periodic points, so Q is the letter after no reason. We can write this as f of xq plus, if it's a one-dimensional map, plus derivative evaluated xq times difference, and this is approximately f. This is by definition 0 because it's a fixed point by this definition. So we have f prime of xq times x So let me call this, and I can't believe it, but I'm again going to be wrong with signs, etc.
I think we got a negative sign wrong in our Taylor expansion. I may be wrong, but that's what.
Here? I mean, right now there is nothing, right? Just Taylor expansion plus other stuff. So far I'm okay, but of course I'll get it signed wrong again. Amazing. So let me call this just f of x. And then this is x minus q. So I have a formula for x is approximately minus, well, it's still plus, f of x. And now, to the order approximation, we will assume that we are doing both things correctly. And we'll call this 1. 0. And it's amazing. And I get a Newton formula which says it's what I used to be, but then I measured the error at that point. That's the value of this function, how far am I from the zero. I divide it by first derivative, and I also evaluate that point. And I get next, hopefully, better guess. So that was Newton. And now what it means is f of the derivative, you pick up 1 here, minus the derivative of the map, evaluate at wherever you are. So if you write in terms of derivatives, it looks a little bit, fixed point functions, it looks slightly longer, but it's the same thing. It just says it's your previous guess it's amazing. I guess I just have a block about Taylor expansion to first order. Minus, and then you compute the error of how distant you are from being a fixed point, and you divide it by 1 minus derivative. Evaluate that point, and that's it. And then you iterate. And then I told you, so this works quite well if your guess is reasonably good. And then I told you that this is a good thing because it doesn't matter that we have a flaw, a relative periodic orbit or something. By the time we have done all the slicing and sectioning, we'll get a periodic orbit. And periodic orbit is a fixed point of, nth iterate of the map. So if I know how to do this, I know how to do everything. And as is so often true in life and mathematics, the simple truth is not a useful truth. And the reason why this doesn't really work so well, this idea that every periodic point it says returns to itself after n iterations of one-dimensional map in this case. That's true, but it's not terribly useful. And to understand why, just think of how you would find the good guesses. So in the chaos book, I use Rosslare attractor to show how you find good guesses by looking at return maps in Rosslare. I can take a very simple example. So let's take this 10th map we had before. So here we have x going from 0 to the 1, and this is f of x. Now plot f of x2, second iterate of the function, because you'll be looking at zeros of the iterate. Now you know that slopes are multiplicative along. This is one-dimensional version of Jacobian. So the slope will be, if it's 2 here, it'll be 4 next time around. So it looks like that. You go from here to 1/4. then what happens to the rest? You know, if you draw it, you'll see that actually the second iterate of the 10th map has 4 branches, and it has 4 fixed points. This one you already had because you already computed it. This one was called 0. This one you already had, you computed it. It was the one here, so it's always going to be here. And then there is a pair called 0, 1 and x 1, 0 that on this map what it does is it does something like that. I'm having an unusually bad morning. I actually slept tonight. I'm sure nobody else slept, but actually, there's a thing that looks like that. And these are the two guys. So indeed, the 2 cycle is fixed points of the second iterate of the map. No problem. Okay, well now I want to find lots of cycles. So I want to find, you know, this one won't be able to draw, but if I go to the nth cycles, you know, this interval will be 1 over 2 to the n. So it's going to be very steep, and it's going to look like this map. And you know, I've chosen this map because I know it has all periodic orbits, so I don't have to worry about pruning, etc. And now, if you're doing a Newton calculation, you're supposed to be accurate just for the silly map. With the initial point, you have to have the accuracy, you know, error in your initial guess in x0 should be roughly 1 over 2 to the n. So the longer they get, the more exponentially precise you have to be. So that's the first part. But the story is much worse, because to get around, you know, the longer a cycle is, every time you come back, you get multiplied by some stretching rate because this map is unstable. So your orbit gets exponentially unstable. So not only your initial guesses have to be exponentially accurate, because if you make an error of that size, you'll find a different solution. You won't find the solution you care. But also you will have to compute them with higher and higher precision, because you're losing precision exponentially. So this beautiful idea that if you know a fixed point, you know everything is useless, because in practice that's not going to work at all. It'll work for a few short periods and you'll be done. So what do? And there is a totally natural way to deal with this, which I used already when I used 3-disk problem to tell you how you find periodic orbits there. See, all your exponential problems have to do with the long time behavior. If you do something for short time, exponential is not a problem. You can do very accurate calculations, etc. So how can you convert this into a short time calculation? So the crudest method is called multishooting. And for maps, that's just what it is. There isn't anything else, but for flows there is a variety of these things, because it's not obvious how often you should shoot. And the idea is that if I know itinerary of my periodic orbits, I know roughly what it wants to do. So I know I want it to be here, and then I want it to be there. Second one, and then someplace else. If I know the itinerary, and that's something we learn how to do. That was the whole point of learning about symbolic dynamics and temporal ordering versus spatial ordering. You know, given itinerary, I can get, you know, very crude guesses could be good enough. So I could just say, I have a sequence, I want to find a periodic orbit that's 0, 1, 1, 1, 0, 1, 0, 0, 1. And now I have to make guesses for the points on the orbit. And the first one, second one. Etc. And I can be so crude, I can just say, well, you know, the first orbit is someplace here, so let me just say it's here. Let me say that x 0, 1, 1, da, 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 is someplace in the interval, but it's on left side because it says 0. And I want the next one to be any place, and just take any point here that I find convenient. Now in practice what you will do is you will already have some understanding of shorter periodic orbits. So you actually use those things that have almost the same thing except the last digit different as guesses. But you could be totally crude. And that's what we did with 3 disks. We just put a piece of rubber. Only requirement was that we went from this to this. That was all. So you can make very bad guesses. And now your computation is, it used to be that you wanted to find a fixed point here, a point Q, and then what you were doing is you took a gun, shot it only once, and it did all kinds of complicated things, and then it recurs close enough by your criterion to where you want it to be, and then if that was true, that was your good guess, and you tried to improve it. But now you'll do something much smarter. What you'll do is you'll guess this point, and then you'll guess this point, and you'll get this point. You'll guess all the points along the trajectory. And now what happens is you start, and it turns out your guess wasn't good, so you made an error. Now you start from the point, and you go around. Your guess is not that good, you made an error. Your guess is not that good, you made an error, and so on. So for n cycle, you can, maybe it's better to draw it just in a plane. You have some guesses what the points look like. And then by actually evaluating the function, so this is your first point in a cycle, x, let's call it 1. And this is f of x 1. Understand, this is all in d dimensions. So I'm just drawing in a plane. And here is my guess. My first guess. I don't know. Here is my guess for the second point. And I don't land there because it wasn't a very good guess. So I have an error. And that error is x x1 2 minus iterate, or short time evolution of my other guess in this family. So that's my error. And now I have n of those, because for every point along the cycle, I try to hit the next periodic point on a cycle, but I miss it a little bit. And I get a list of errors. And now what I would like to do is I would like to minimize the problem, just like I did before. So before, what we did is we tried to find a better guess that decreases the error. Now I have a vector of points. Cycle is of length n. So now my guess will act on this vector of points. And so now the Newton says, okay, I have a vector of n points for n cycle. So this is n-dimensional vector. Right. And it depends, this vector, this x is n-dimensional. These are all the points along the cycle. And at the moment we're assuming this is still one-dimensional map, but that's just a detail. It works in any dimension. So x1, x2, xn. And what it is it's the matrix of my errors. I would like to make the zero. No, the vector, collection of my errors. So it's comparing x1 with the preceding point. I'm on a period n, so the preceding point, when you're in periodic orbit and you have periodic points. So this is 1. If you have n of them, this is n2. So the preceding one is xn. Then x2, that's what I tried to reach by starting at periodic point 1, and xn. Xn minus 1. Right, so this is matrix of misses. No matrix, I mean vector of, how far did I miss? Whatever. There's a way to reformulate this very nicely. You can just square all these guys, add them up, and call it an error function, and then you can motivate this as a Lagrangian, call this Lagrangian, and have Lagrangian multipliers, etc. But I won't do it this way, but it's totally elegant and general, and that's what it means. And now the game is to minimize it. And again, the thing works the same way, but now you have to keep track of errors of matrices because you're multiplying, and they will not be commuting when later on when you need to have products of them. So taking the derivative of this, that's a n by n matrix. And you get, in a Fourier series, you'll get the same thing as before. This will be your current. This will be your guess for the new thing. And for some reason, which I'll let you ponder, I have minus sign. But this minus sign could be Burak's fault. I'm not saying anything, but just in case. So now this is a matrix. And this is kind of matrix that people who do numerics really like, because when you look at it, it's a very sparse matrix. You can just evaluate it. And what you find is this depends on the first guy, so there's a 1 here, and clearly there'll be 1s on diagonal every place. You can see that. Then the derivative shows up in the nth place, and that's because you have a cyclic solution. So there is a minus f prime evaluated x n, and then This one is just preceding, so that one shows up here. And this is the matrix. And this will be f of x2. Again, this is a matrix denote. So you get a banded matrix. You have a diagonal and one band below the diagonal. Yeah?
Wouldn't, just to be sure I'm on the same page, wouldn't that matrix F would have to have d columns like the dimension of the vector instead of n?
Yeah, right now what we're doing is we're still doing it for one dimension. But you're absolutely right. When x has become n-dimensional vectors, then you have to make it d-dimensional, you know. So right now I'm just doing a map like this. I'm saying I have dimension on a unit interval and how I would multi-shoot.
Okay, so
So-
I'm having trouble to visualize the column. What the second column of this matrix is the derivative of the second variable?
No, it's this derivative, right? Because you just have a map on unit interval. This is the map, tuk, tuk, tuk. And this is computing its derivative.
Okay.
Just that. But you're absolutely right. You know, the next step, when you think about it, you can actually make this for points in d-dimensional space. And then this matrix will become Jacobian matrix, the one that we have. So it'll be, you know, the new matrix. So I'm doing it in two steps. I'm saying if you're looking at something that has period n, it's actually better than, instead of looking at the fixed point, think of all periodic points as a set, dynamics as something that moves it by one notch, and then compute the error matrix from your guess to the true thing. So just to motivate it. And the reason for that is that for a short time, usually these derivatives that show up here are not enormous. By the time you get to a long periodic orbit, you multiply them all, and then they can be outside of your machine precision, right? You can find it, you know, orbit over 10 is unstable with 1. By the time you come back, the errors grow by, you know, 10 to 137. And you can always find sufficient long orbit for which it will happen, you know, because they're all exponentially unstable, and the instability is multiplicative with the length of the orbit, or, you know, additive in the logarithm of the orbit. So these things can grow very unstable. But if you trade it in for n-dimensional space, it becomes something very simple and controllable. And there are two advantages. One is that you control the itinerary, and second, it's very robust because the instabilities are very cheap, very meek. Because, you know, maybe in one iteration, my neighbors go by a factor of 2. Yeah, I can deal with that. Yeah, I'll write it, but not quite now. But that's the main thing. The main thing is that it's true that when you have a fixed point, everything can be thought as, every solution is a fixed point, but it's not useful way to think about it. The more useful way to think about it is that you have orbits, so these are sets of points reached by dynamics, and you're trying to compute that orbit. And even though initial value problem can be very unstable, if you take any point on the orbit and go around, errors can grow beyond the bound. The orbit itself is a very robust object, because, you know, everybody's moving by small steps, and in continuum case by infinitesimal steps. So it'll be very robust. So multiple shooting is the way to go, and it's easy to program. You know, it won't kill you to do this. And you know, I don't think I'll waste your time programming this, because you probably have to compute 0 of something sometimes in your life, and, you know, this is an example how you do it of some function. This is specific to dynamical systems, but doesn't matter. So now, this is great. It says that even though my dynamics can have lots of unstable solutions, and it's impossible to find them by experiment, because when I try to find them, everything falls apart, nothing stays around. It turns out that the unstable periodic orbits of these sets are actually very robust and very stable. And they can really computable. You just have to think a little bit more about what you're doing. So, the way I think about it is that if you have a sink, a stable thing, it means you throw something, it all falls in a hole. Now think of the unstable things as wedges. So you're trying together and you just get pushed away by the edge of the wedge, and you're trying to find the knife edge. And the way you do this is you keep exploring it until you get a good bracket. So it's actually very easy to see experimentally if you think that way. If you have an unstable solution, you can measure deviation on both sides. You can find it. And the more unstable, the more easier it's to find, counterintuitive. Now, this is great. So but we don't care about maps because we care about Young-Mills or general relativity or something that's written in terms of differential or partial ordinary differential equations. So the maps are useful idealization, but how do we do this for flows? And this is the thing about this book. When we wrote it originally, we assumed that you know everything that I'm talking about until this point in the course, and the book actually starts next week. All this was just something everybody knows. But when you try to do it, there's lots of thinking that goes into it. So having this thing is so one thing that you might have found unnecessarily annoying is I keep obsessing about continuous symmetries, and it's okay, we have continuous. What's the big deal? It turns out that if you don't think about continuous symmetry here, it'll be very hard to find invariant solutions, periodic solutions. And the problem is, and one doesn't appreciate it until you start computing with it, we have shown that whenever we have an invariant set in time, associated with it is the marginal direction. So the velocity at every point, which is tangent to our curve, at every point on our orbit is eigenvector of the Jacobian. So this is prime periodic Jacobian with eigenvalue 1. And that's totally obvious because any neighboring points, when they come back, their distance is identical, so there's no multiplication along that direction. And why do we care? Well, we care because what happens in this formula is we have a 1 minus derivative, which will later be Jacobian, but especially easy to understand in the case of one-dimensional map. So if this thing has slope 1, where you're interested in, then this will diverge and I'll have no Newton convergence. I have no method. So actually it's a big deal that whenever I have marginal eigenvalues, and they also have to do with the group factors as well, they're also marginal. Because doing symmetry transformation doesn't change distances of things. So the marginal things are trouble. And you have to get rid of them. And I told you the way you do this is remove all the continuous symmetries and then remove also the time symmetry by using Poincaré section. And that's okay. You know, if you get into the Poincaré section, what I described here will work, because this is true for all the maps. So map came from Poincaré section. But in practice, it's not very smart, because Poincaré section is totally arbitrary. You know, you tend to define them so they capture some important global properties of the floor, etc. But here we are doing local calculation. We are just trying to find in small neighborhood what's going to happen. So it doesn't really make much sense. When you use Poincaré section, that doesn't make so much sense. There might be a better intrinsic method to do it. So let me first explain the trouble. So now, when I have a flow, and I make a guess for periodic point. So suppose I have a real thing. You have here there is actually a periodic orbit P that I'm trying to find. And I'm making a guess to some point close to it. So what happens is that if I have a pretty good guess, this thing will go with it, do something. Then, if the thing is unstable, and that's something we care about most, I will get here. And I have two problems with my guess. Here I had that x of f of x going time t around comes back exactly. But here I'll have a problem that delta x will change. So that'll be the difference of integrating for the same period around, starting with my initial error, the one that we used to define the method. But I will also generically fall short in time, because if you take a different path, your velocities are different and you don't come back at the same time. So there'll be also a problem that I really have to compute correction to the time to get close back. Otherwise I might have shot by, or I haven't quite reached the point, etc. So now I have my usual condition that says 0 is plus f t of plus dt of x plus delta x. Saying that if I'm some distance from this thing, I don't know, I should call it delta x, but if I'm some distance from this thing, by the time I come back corrected for the time of arrival, so I get close, as close as possible, for example, and determine dt this way, I get a 0. So now I have one equation, but there are two unknowns. I have to compute delta x. And I have to compute a time correction. Because when I start looking for my periodic orbits, I don't know its period. So I'm guessing what it is, and I have to improve both the period and the location. And in d-dimensions, this is actually d plus 1 unknowns. So that's one trouble. The other trouble is that when I look at this formula,
There should be a minus sign like that.
In front of f.
right here, that would sound better, right? because I'm measuring the distance when I come back. So I would like this to be 0 once these increments have gone to 0. So minus sign totally crucial.
Excuse me, and you define coming back by the minimal distance?
Well, I have to tell you, see now it told you that there are two things going on. Is, you know, I'll make an error in space, but also because this is a flow, I have to do something with the time, because times of arrival for neighboring trajectories are not the same as for the trajectory I'm trying to get. Now, how I define both of these guys is the next step. But I already kind of told you one thing that might make sense. If there was distance, then I would like to use delta t when I have make my closest passage. So that seems natural. So that's one way to do it. I have a curious section on d-dimensional maps. And my section says it's just like this. So it's one paragraph long. So if it's d-dimensional state space, then everything looks like multi-shooting was looking before, but now d dx, the matrix that we had to compute, is it's n cross n for every point, and then every point is d-dimensional. So multi-shooting matrix will look the one like the one I wrote before, but what it will have when I write it out it'll have identity in each diagonal d-dimensional block. And then this thing, 1 minus f, will be called 1 minus Jacobian for computed on one return. That's what it will be for the maps. You know, starting at point xn, etc. 1 minus. So it all just simply propels into d dimensions for the maps. And now when I look at how the Newton would work here, I would need to compute this matrix because it'll show up in my Newton iteration. And I'll need the inverse of this matrix. Now, inverting this matrix is a trouble because I know if J is computed on a periodic point where X is in the cycle, you know, one-dimensional set of points which are this periodic orbit, I know that this satisfies this equation. It has any place on the orbit, the tangent is a unit eigenvector, just one. And now, if I try to compute 1 minus JP, which is what I need here, if I try to invert it, which is what I need to do, this is going to be trouble because as I approach my solution, this thing is developing a zero eigenmode. But you know, I cannot invert a matrix that has a zero eigenmode. So I have to do something to deal with this situation. Now, dealing with this situation is fairly easy. And we have some experience, actually this week's problems that helps already. You know, let me say, how am I going to define this delta t? My problem with the marginal eigenmode is that I'm not allowed to vary along the trajectory, because any variation along the trajectory causes no change. That's the original mode. So I need a condition that says I'm restricted in my variations. And there's an obvious condition here, if I have some kind of norm, which says that I will allow conditions, variations in dx at this point here, only if they're transverse to the local trajectory. So that's this very natural local thing. And what we are really doing is we are saying, well, locally every place we'll just make a little Poincaré section, very small ones, designed so it's orthogonal to my trajectory. So now I have my original equation and one constraint. So now I have a set of equations, and this works out to be 1 minus j computed at x. I'll first write it and then we'll check it. And now I have a well-posed problem to solve. It's minus the error. And this error in this form is, I want to minimize where I get along in the cycle. So this is Ddimensional. And I want the time to be just right. And time being just right means I want time such that when I return, I left the neighborhood, and now I've defined a local constraint for variations. So this is b wherever I am. So I'm only allowing d minus 1 dimensional variations by this. And when I come back, I'll fall maybe short of this trajectory. So then I have to make up for the rest of trajectory, and locally every trajectory is linear. So motion along this direction, along trajectory, is really just velocity times dt. And it's all good to leading order, so we make it at a final point. So now what we have is, we have a calculation in which this is how transverse error grows. It's being multiplied by the Jacobian. And then there is a bit of error that has to do with moving along the trajectory. That's v dot dt. And then I have a constraint that I demand that my variations are locally orthogonal to 0, so that's how this came about. Now there are variants of these things, so here I've decided to use the local way of putting transversality, saying I'm moving with my rocket, I just look at my neighborhood, and then only natural transversality is something that's orthogonal to my orbit. But if I had some global section, this would look slightly different, but it would be the same spirit. So now we have increased our system by 1 dimension, but we're actually computing the correct solution in 1 dimension less. because to make it, d minus 1 dimensional, to make it what we know about fixed point in the map, we have to also adjust the time. And that's what this thing does. So now, it might not be obvious that this matrix doesn't have marginal eigenvalues, so I'll leave it to you to ponder that. But basically, by having gone to the bigger space and constraining everything in this way, you solved the problem that you had before, which was that you couldn't invert this. You couldn't actually write the inverse of this matrix, and therefore you couldn't predict the new increment that improves your guess both in space and time. But with this extension, you can make it bigger. I mean, you can invert it. Now, in practice, it depends on your problem. In low-dimensional systems, people actually just invert this. In high-dimensional systems, there are all kinds of tricks about how to avoid inverting this and still compute improved. See, what happens in high-dimensional systems, you might not appreciate it, but when we look at exact solutions, exact periodic solutions, for example, of Navier-Stokes equations numerically, and we do this in Fourier, Chebyshev, etc., then it turns out this matrix has 10 to the 13 terms, algebraic terms. So we can't even put it on a computer, let alone invert it. So then people realize that in some situations it's better to maybe evaluate numerically these derivatives rather than kill yourself. And that's called Arnoldi, Krylov, etc. So this is how you do it for the fixed point, and then the whole thing again works equally well if you do it as multishooting. So if you do it as multishooting, this thing becomes a large matrix, and each block is d-dimensional block. So this is d cross d. And you have to compute the Jacobian. So it's a minus Jn at the periodic point. And then it marches off as a banded matrix in which these blocks are d-dimensional go on, and because of periodicity, you get here a thing minus Jn. So there is a block that looks the same way for the map and the flow, the just generalization of multishooting for one-dimensional map. But now you have another block because you have to get velocity fixed every place. This guy here. At first point, at second point, diagonally here, And then there is another block which generalizes the zero, which says I have to get my transversality in d dimensions guaranteed. And then for every periodic point, again, you might get v, blah, 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 blah. Just like that. And this now acts on your d guesses in d dimensions where your thing should be. Oh. One. So these are d-dimensional vectors, and there are n of them. And the rest of these times, sorry. Then you have to fix the times for every hop as you're going around in your set of guesses in multishooting. So this is n times d-dimensional vector, and then you need n for this one continuous symmetry. And the equation you're solving is you find the errors in the time, you impose them exactly, and in the space you compute the value of these functions, error functions, which are measuring the deviations. You know, how bad your guess is. And basically, by the time you've gotten it to work for one-dimensional map, and gotten multishooting to work for one-dimensional map, going to d-dimensional space is really not a big deal in programming. You just add new information. So you replace what used to be 1 by 1 matrices by d by t matrices, but it all goes. And that's it. Throughout the calculation, that's all.
There is one other thing. So in the first line, you have minus v of x, but technically it's not v of x, it's v of f of t of x.
Yeah, so the way it got there, so I went a little bit too fast. So the way it got there is that I had to do two expansions, right? So I had to write this using the group property of the flow. I had to write this term here. I can write as f dt acting on f of t of x plus delta x. So that's just identity, right? Then I can write for short time what f is. It's an integral of wherever I started plus delta t, delta tau, 0 to t of the velocity evaluated at time t. So that's local vector field, and that's trajectories, it's an integral. And for short time, I replace this by delta t, just velocity itself, assuming that time is sufficiently short that then this flow is sufficiently smooth. So that gave me and this is where I come. So this is so this becomes ft of x plus delta x plus delta t of f of t x plus delta x. So this one will now give me Jacobian. And this term, I can cross out the extra guy. And sorry, this is the velocity here. Velocity, right. And that's where this now erased term came from. I guess I erased it, but this is where this term comes from. Is that okay? So I go around and I come close to it in time. So I split out the time as a short time evolution. And short time evolution is where I started, which is here, plus a little bit times velocity. I think it's important, so let me try to do it. It's going to repeat itself every time you have continuous symmetry. So you might just as well try to get it right first time. So I'll just write, what this picture means. So this picture means that I look at original time. So I look at my initial point, x, 0 here. Then, to get to here, I evolve it for time I guess, let's see. I look at my original deviation from the correct answer. There's a correct answer here. This is the point on periodic orbit that I'm trying to get. So look at my original deviation, which is x0, well, just call it delta x times 0. Then I run around and I guess I run around. Good recurrence time is delta time t, but actually as I'm improving my guesses I have to keep varying this thing, so there is a delta t here. And the object that I'm trying to minimize, function f, is delta and when I write this I'm assuming that I'm putting the origin at whatever the solution is. Bear with me because that's not so important. So now the only trick is that I have a constraint which allows delta axis to be only in this plane. But this map won't get me to this plane unless I have the right delta tau. So I have to expand this in both small variations. And the way I expanded this, I use the abelian nature of the time. So I say I first get to f of t delta x0. So that's just an identity. And then I say this thing is the same as having started at this point f of t delta x0 plus having gone a small distance. So if I'm trying to go along the orbit, so this is delta x longitudinal, the way I compute this in time delta tau is I use the velocity at a point times delta tau. So when I get here, this point is my original point x plus delta t times the velocity at x to the linear order, to the leading order, right? So that's what integration along the trajectory does for short order. It takes wherever you started, and then it just, in linear approximation, just takes the velocity and multiplies by elapsed time. And that, that's kind of Eulerian integration of the order. You get that phi. So that's what we do here. We say it's delta t plus times velocity. Now this is the dimensional vector. This is the dimensional vector. This is just a number. And this is a length. And dimensional, and this is all. If x is a length, this is dimensional. Now we have equals delta x. Now this is, computed at delta x by definition, right? But now I have two small numbers. So in the leading, size of all deltas approximation, this is delta x0 minus f t delta x0 plus delta t V0. And the reason why 0 shows up because I've chosen to put my coordinates at the equilibrium point. But, you know, to the same approximation, it could be whatever I'm computing in the neighborhood. To the order, leading order in deltas, right? And now this thing, I know what it is. It's Jacobian, right? So I get 1 from here minus the Jacobian evaluated in time t, having started again at 0 or in this small neighborhood, times delta x, 0, plus v 0 times delta t 0. So these are these two terms. The first one gives you that. And the second one gives you that, and you know, of course I have a minus sign problem. But
So my problem was not with,
oh, there should be a minus sign because there's a minus sign here. This minus sign I can get. Ah, wonderful.
it was with the argument to the flow in the first line. It's not the initial point, it's your final point.
Yeah, it's, you know, initial point plus the deviation.
No, it's the initial point evolved back onto the map. It's f.
That's the velocity as the final point.
Yeah, it's a velocity at the final point, but because it's multiplied by delta tau, I can be fuzzy and decide at which final point
It makes
to
a
compute.
difference.
So what would you like? Just the velocity at the final point?
Yeah.
Okay. So if it makes difference, we put delta x here. So it violates the laws of epsilons, but sure. You know, it just means that final point is some distance away, right? So it's
That's x plus delta x isn't it?
well, but you know, I chose coordinate system where the periodic point is at 0. In other words, I'm choosing the cowboy frame. The cowboy is moving locally. Every coordinate system has origin at the periodic point. I'm allowed to do this. I can move it around. Just save some notation. And then what happens is the deviation gets amplified or diminished by Jacobian, depending on what eigenvalues and eigenvectors Jacobian is. So that's this term. And the thing that you always get in periodic points, you actually have to look at the difference where you were minus the deformed thing. So you always get minus Jacobian. And now because we have a constraint in defining delta x, we actually have to move also the longitudinal part of the trajectory. So it's in the allowed space, and that's the longitudinal deviation. And are you okay? Or okay. So now, you know, basically, it's like as in love and war, you know, everything is allowed as long as you go out there and come back with the fish. So the only goal of this game is to take something that's unstable and looks undoable and produce an algorithm which makes it stable. So what you're really doing is you're just producing algorithms where the point that you care about in the new version of your dynamics, because now you have a fake dynamics, you're adding Newton to you, who nobody asked about. But this modified dynamics has a property that you attracted by the point that you want. So now you look at this and you might decide that it's very expensive to compute these Jacobians. Maybe I can find some finite matrices that do the job. Or so there's a whole bunch of things that all look like Newton, but they're just modified, and in a ways that might be good for a particular problem. Maybe it's very hard to compute something, but you can estimate it. So people compute Jacobians few times in calculation. The price you pay are always, the Newton is amazing because it's super exponentially convergent. So if it works, every time you iterate it, you get twice as many digits. That's sweet. But if you screw it up by not doing what it says you should do, then it converges slowly, but it'll converge. As long as things converge, you're very happy. So, so there are these two things. One is we're trying to find zeros of functions, and there are lots of methods to do it. And Newton says I use linear as information. There might be some other information I can use about it. And then there is, totally radically different, I think much deeper way to think about this, is that you're never trying to find these points because they don't mean anything by themselves. They only mean something as invariant set. Periodic point by itself is nothing. It's the whole set of the points that's important. They sit in the state space, they tell you this happens, that happens. So these sets are important. So then there is a wholly different and profoundly more deep way which you have learned but you don't realize of thinking about this, which is how do you compute some property of a set? How do you make a set? So that you have learned in mechanics is as variational calculus, so come from Apertius and then from Lagrange, etc. So these problems have been solved. And they're used always in engineering. There are many, many optimization problems. So, to you Lagrangian looks sacred because there was Newton and now there's Lagrangian, right? But its mathematical structure says that, and it might have puzzled you, why the hell would you do this? Because if you have Newton's or Hamilton's equation, you can integrate them forward in time, you get an answer. So why do you keep getting taught all the time that you should be varying the paths and looking at extrema of Lagrangian path, etc.? The reason why they torture you with this in classical mechanics today is because you can't learn quantum mechanics without it, because it's totally essential to understand variational principles in quantum mechanics. So to understand semi-classical WKB, etc., you need it. So that's one of the reasons why you're taught. But the thing is really deep. It says that there's an invariant set. I don't care about any single point. I want to get the whole set. And it's so dear to me, I'm willing to pay so much per foot of the periodic orbit or something. So then I'll assign a cost function, which will say, if I deviate this way, that's okay, it doesn't matter much here in the orbit. If you deviate this way, it really costs a lot. But if you deviate in stable direction, it doesn't matter very much because it's going to heal itself, etc. So when you really, really start doing this, you might consider variational methods, which are much deeper. And they're actually practical. They're not just things in the book where you, take a variation and look extreme and get Lagrangian equations of motion, compare how, blah. This is all great, but they're much more general than that. And they're stuff you want to use. So it might be easier for you to be in 100,000 dimensions because computers, have memory now, and take 1,000 points on your orbit. And then what will happen is when you look at this matrix here, this matrix will look very banded again. It'll be very thin matrix because it turns out in short time not much happens. It's only in the long time that this matrix gets filled up. Jacobians get filled up only a long time. So it might turn out that, not only you can do it, but it's actually much faster to do it that way than forward in time. So this is the end of this local story. And this is coming out just fine. So now what we'll do from now on, we go into the big world.